Hello, everyone. I'm Rong Chu from Purdue University. The title of my presentation is Heterogeneous Beam Element for Multiscale Modeling of Composite Beam-like Structure featuring spanwise heterogeneity. In a real engineering application, we want to model beam-like structure in structural analysis. Typical multiscale method will require us to find a structure gene known as SG, which is defined as the smallest structure that repeats itself in the macroscopic analysis. For the left side rotor blade, for example, the SG is the 2D cross section. For the right side honeycomb beam, the SG is the 3D structure. We then homogenize the SG into Timoshenko beam properties or Euler-Bernoulli beam properties. We then input these properties into beam element in macroscopic analysis and get a structure response. However, this kind of traditional multiscale method has its limitations. For example, there is no so-called repeated structure in the wind turbine blade. A traditional approach would be cut the wind turbine into multiple cross sections and extract the beam properties in each cross section and input those properties in macroscopic model. This traditional method would assume the beam have uniform cross section in each beam element and thus cause inaccuracy. We want to have a new multiscale method to deal with this problem. Here we present our new theory, heterogeneous beam element, as known as HBE. HBE is to homogenize a microstructure. A heterogeneous system described with many meshes needed for describing microstructure details into a single 3-node beam element. In other words, in conventional homogenization, we want to get the 6x6 Timoshenko beam properties, but here we want to directly get the 18x18 element stiffness matrix for 3-node beam element. And we use this element stiffness matrix to run macroscopic analysis. We would utilize the principle of minimized strain energy loss in the homogenization process. After we have the macroscopic result, we input displacement of each node for each element to calculate the strain and stress in each element. So we can conclude the workflow of HBE. In HBE, multiscale modeling of a beam structure can be divided into 3 steps: homogenization, macroscopic analysis, and dehomogenization. In homogenization, there are 2 sub-steps. First is to compute the fluctuation function of the boundary surface, and then calculate the 18x18 effective beam elements matrix. We then input the beam element stiffness matrix via Abaqus UEL and run the macroscopic analysis in Abaqus to obtain the displacement of the beam elements. Finally, after we have the macroscopic displacement, then the local displacement, strain, and stress field of a SG can be recovered by dehomogenization. Here is our first example to solve by HBE. It is a composite cantilever beam with dimensions this here. Here is the layout and also the material properties. The beam is subject to a tension load and a torsion load. Traditional multi-scale method will require would use the 2D cross section as SG and homogenize it into Timoshenko beam properties, and then input these properties into the macroscopic model. For the HBE model, first we identify the SG from the original structure. Once we have our SG, we then extract the cross section of the structure. Then we extract the fluctuating function from the cross section, input it back to the SG, and run the 3D homogenization for effective beam stiffness matrix. Then we input the beam element stiffness matrix into 10-element macroscopic model via Abaqus UEL subroutine. We run a direct numerical simulation model as a benchmark. We call it DNS model. Once we run the macroscopic analysis, we would have displacement of the macroscopic model. We can use that displacement to run the dehomogenization and get a local stress field. Here, we define a path, and we see the stress distribution along the path. We only list 3 stress fields here as the rest of the stress are zeros. We can see our new method, HBE, has perfect match with DNS model, and so does the traditional method. Our goal here is to show that the HBE can reproduce the result of DNS when dealing with periodic structures, just like traditional approach. The second example is a tapered homogeneous cantilever beam made of steel. The beam in the minus x surface is 20 millimeters wide and 10 millimeter wide in the positive x surface. The beam is 100 millimeters long with 10 millimeters uniform thickness. In this case, we test 2 loadings, tension and torsion. Here, we also run a direct numerical simulation model as a benchmark. Then we have our HBE model, in which we have 4 SG, and we homogenize each SG into a single beam element, and we input them back to the macroscopic model in Abaqus. For the traditional approach, we have 4 cross sections, and that can represent the 3 structure of each segment. Then we run the homogenization to get Timoshenko beam properties of each segment and input those properties into the Abaqus macroscopic model. Here, I would like to demo the displacement result first. We first check the UX displacement in the reference line. The HBE perfectly overlap with DNS, and the traditional method has its good accuracy. However, for torsion load, we see that more obvious improvement of HBE over traditional method. We see that the HBE perfectly captures the UY and all the non-uniform parts. However, for the traditional method, we see that the displacement curve is composed of 4 straight lines. This is due to limitations such that each segment of traditional method has uniform cross-section in macroscopic analysis. Here is the dehomogenization result for tension. We see the HBE capture and the trend much better than traditional method, which only returns stepwise behavior. We also see that the HBE can capture the behavior at the boundary. Here is the result for torsion. Again, HBE is pretty accurate in stress 1, 2, and 1, 3, and traditional method would only return the stepwise behavior. And finally, this is our conclusion. We have heterogeneous beam element, HBE theory, and the code to homogenize heterogeneous beam-like structures into equivalent 3-node beam elements, and dehomogenize for local displacement, strain, and stress fields. And macroscopic analysis with HBE is more accurate than traditional approach for aperiodic structures. HBE has more accurate local stress fields than traditional approach. This is my presentation. Thank you for your listening.